Ever wonder how your phone can instantly spot a face in a crowd of photos? Or how a self-driving car weaves through a totally chaotic street? Well, it's not magic, not at all. It's a fascinating field called computer vision. And today, we're going to pull back the curtain and break down exactly how machines are taught to see our world.
Okay, so take a look at this. To you and I, it's obvious, right? We see a bus, we see some cars, trees, a road. But to a computer, this is just a meaningless jumble of data. So how in the world does it go from that raw data to saying with incredible confidence, yep, that's a bus and I'm 92% certain? That's the big question we're going to answer right now.
And the key to solving this mystery lies in a field with a pretty straightforward name, computer vision. This is the science, the engineering, all of it behind giving machines what feels like the superpower of sight. To put it simply, computer vision isn't just about showing a machine a picture. I mean, that's the easy part. The real goal here is to get them to understand what they're looking at, kind of like how we do. It's all about pulling out the important, meaningful information from all that visual chaos so the machine can actually do something useful with it.
So if we want to get how a machine learns to see something like a bus, we've got to start at the very beginning. We need to understand what a machine sees on the most fundamental level. And believe it or not, it all starts with the humble pixel.
That's right. Every single stunning photo you've ever seen, every high-def video you've watched, it's all just a giant grid of tiny, single-colored dots. We call them pixels. Millions and millions of them, all lined up in a perfect rectangular array to trick our eyes into seeing a complete picture.
But here's where it gets really interesting. For a computer, a pixel isn't red or blue. It's just a number. It's called a pixel intensity value. So in a simple black and white picture, you have one number for each pixel. 0 is pure black, 255 is pure white. For color photo, you get 3 numbers for every single pixel. One for red, one for green, and one for blue.
So let that sink in for a second. The most important takeaway is this. When a computer looks at that photo of a bus, it doesn't see a bus. It doesn't see a street. It sees a massive grid of numbers. A matrix. That's it. Our entire beautiful visual world, to a machine, is basically just a giant spreadsheet.
Okay, so if an image is just millions and millions of numbers, how on earth does a computer find a bus in that ocean of data? It can't possibly look at every single number, right? It means a smarter way. It has to find the important patterns.
And that smarter way is a process called feature extraction. The whole idea is to simplify everything, to throw away all the noisy, unnecessary pixels and just keep the absolutely essential characteristics, the features that really define an object. We're talking about things like edges, corners, and textures.
Just look at this. It's a perfect example. On the left, a normal, full-color duck. On the right, we've stripped out everything, the color, the texture, all of it, except its edges. You can still tell it's a duck, can't you? Of course. That simple outline is basically all our brains need, and that just goes to show how incredibly powerful a feature like an edge can be for recognition.
So, what even is an edge in the language of a computer? Well, it's not really a line. It's actually a mathematical event. It's any spot in that grid of numbers where the pixel values change really fast. Imagine a low number, like 20, right next to a high number, like 220. That sudden jump, bingo. That's what a computer flags as an edge.
All right, so we know we need to find these edges, but how do we do it systematically? How do we find every single important edge in an image? Well, for that, computer scientists have this incredibly elegant and powerful mathematical tool called convolution. Convolution is pretty much the engine that drives all of modern computer vision. It's a formal operation where you take your huge image matrix and you slide a tiny matrix, called a kernel, over it. And what you get out the other side is a new matrix, called a feature map, which is basically a treasure map showing exactly where that specific feature popped up.
You can think of a kernel, sometimes it's called a filter, as a tiny little detective or a specialized magnifying glass. It's designed to find only one very specific thing. For instance, one kernel might be built just to find vertical edges. Another one is designed to only find horizontal edges. By using a whole bunch of different kernels, we can scan an image for all sorts of simple, fundamental features.
So how does it actually work? Well, it's a surprisingly simple rinse and repeat process. You take your little kernel and you place it over a small chunk of the image. You multiply the numbers that line up, and then you add all those products together to get one new number. That single number, that becomes the very first pixel in your new feature map. Then you just slide the kernel over one spot and do it all over again, and again, and again, until you've covered the entire image.
Now, it's worth pointing out that before this became the standard, vision experts had to design these feature detectors by hand. It was this incredibly difficult, brittle process. You might spend months perfecting a detector that works in sunlight, and then it would completely fail on a cloudy day. The absolute revolution of using convolution inside a neural network is that the network learns the best features by itself. It figures out the most useful patterns automatically, which makes it unbelievably powerful and adaptable.
Okay, this brings us to the final and maybe the coolest piece of the puzzle. We know how to find simple things like edges, lines, and curves, but how does that let our machine recognize something as complex as a car or a face?
Think of it this way. These simple features are like the Lego bricks of vision. A single line or a single curve isn't very interesting on its own, but when you start combining them, well, that's when the magic happens. A couple of curves and lines might form an eye. Combine two eyes and a nose, you start to see a face. A collection of specific lines and circles becomes a wheel.
And that is the job of something called a convolutional neural network, or a CNN. It starts by running a bunch of convolutions to create dozens of these feature maps, one for vertical lines, one for curves, one for greenish textures, and so on. These simple maps are the input. Then, layer by layer, the network actually learns how to combine them into more complex ideas. It learns that a circle on top of two smaller circles often means a wheel, and that four wheels plus a big rectangle is probably a car. And this is the most amazing part. Through training, the network actually teaches itself and refines the kernels, figuring out the absolute best features to look for to get the job done.
And that brings us all the way back here, full circle. We've just walked through the entire journey. The computer starts with the raw image, that giant matrix of pixel values. It applies convolutions with kernels to create feature maps that highlight basic stuff like edges and shapes. Then, a deep neural network learns to combine those simple features into a complex concept. And finally, it spits out a label, bus, with 92% confidence. Mystery solved.
So we've successfully taught machines how to see objects. It's an incredible achievement. But the next great frontier isn't just seeing, it's understanding. Understanding context and intent and meaning. And that raises a really huge question, not just for engineers, but for all of us. As this technology gets woven into the fabric of our lives, what exactly should we be teaching our machines to truly understand about our world?